recording. Okay, there we go. Now we're recording. So, excuse me. All right. So, where are we? I have graded your. I'm a little behind on grading, as is usually the case, but I am caught up on the topics that are going to be retested this week. So topics I and J are fully graded. If you haven't yet, please go ahead and look at your feedback. Look at the feedback I gave you for your work on I and J. I think that we should review J. I think that we should review some topics from I and J, and I think we'd better dive into some work on transformations as well, because transformations are an important topic coming up this week. So let's quickly review what it means to compose and decompose functions. Okay, so I'm going to get the whiteboard up. All right, so first, what does it mean to compose two functions together? I'm just going to go over the problem from quiz I, because it's a good one, and I might as well. So on quiz I, problem 1, we had these two functions. There we go, two functions. And I asked you to compose f composed with g, like that, in that order of x. So that means you're going to do f of g of x. So when you have f composed with g in that order, it means f of g of x, like this. So the order these come in is the same order they appear in when you put one inside the other, like that. Assuming you're writing from left to right here. So that means that in this order of composition, we're going to be taking the g function and putting it inside the f function. So this inside here, we have inside our f function here, we have g of x, right? And g of x is equal to this, x plus 1. So the x plus 1 from here is going to go inside the f. That's what we're going to have inside f. So this is going to become f of x plus 1, like that. So the whole idea of composition is to put one function inside the other. So essentially now we're evaluating our f function with x plus 1 as its input. And remember that what that means is that we're going to write out the f function, which is, based on this here, it's going to be 2 times blank divided by blank plus 5. Right? Remember, you write out the f function with a sort of a blank input in place of its x variable, right? Every time there's an x, you replace it with a blank. And then what we're going to do is fill in that blank with whatever the input is. So in this case, it's x plus 1, x plus 1, x plus 1, like that. This is what it means to compose two functions. You're basically putting one of them inside the other one, and taking the output of one and giving it to the other one as an input, right? It's not multiplying. I think the most common mistake I saw was people just not knowing what this was and thinking they're supposed to just multiply the two functions together. That's not what this is. Okay, if I wanted you to multiply the functions together, I would have said multiply these functions together, right? Like that would be written like this: f times g of x. You can write it like that, which means f of x times g of x, like that. That's multiplying. That's not what we're doing here. So this is the correct way to compose them. Now there is a little bit of simplifying that can be done here. You can distribute the 2x plus 2. Then in the denominator, you can do plus 1 and plus 5. So plus 1 plus 5 is going to be plus 6 overall. Now this is done. There's actually no further simplification that can be done on this. One of the other most common mistakes I saw on this problem was canceling something, attempting to cancel something. A lot of people tried to cancel out a factor of 2. But even though you can factor out a 2 in the numerator, even though you have this 2 that was here in the numerator, there is no factor of 2 that you can pull out of the denominator, right? Because even though 6 is a factor of 2, this x itself doesn't have a factor of 2 in it. So you can't find a common multiple of 2. You can't take out a common factor of 2. And the most important thing to remember here is that you can't cancel via division anything unless it's a factor. Okay, and it's very important to understand what the word factor means. Factor means that it's part of a product. A product is when you're multiplying two things together, right? Or two or more things. You're multiplying things together. The things that you're multiplying are factors. You can't cancel anything unless it's a factor. I'm recording, otherwise I might have said that a little more strongly. I wanted to throw in some strong language, but I didn't. It's a factor. It's got to be a factor. This is one of the most common. It's one of the most common mistakes is just not understanding when canceling is okay and when it's not. And I think it helps a lot to actually understand the vocabulary. I said this in my very first video I ever gave you, which is sort of like the review video where I'm like, hey, let's review what these words mean. It's really useful to have words and know the words for the things that we're talking about here. So if you don't know what a factor is or a term, if you don't know what a product and a sum are, review those vocab words, okay? Because I think having words and knowing what the words are helps you understand and remember these things. Questions on this problem 1 from topic I? Questions on this one? You're all very quiet today. It's because I'm recording. Unless you're just quiet because I haven't seen you in a week.
So it's like the 2s we got with our final answer. Is there an extra plus over 2s plus 2, or is it, what is that, times 2? What is it?
2x plus 2.
Okay.
Yeah, Modema, your question about the here it's multiplied, right? Here it's 2 times x plus 1, but here we're saying, after you distribute that multiplication, you have 2x plus 2.
Okay.
Does that answer your question?
Yeah.
Should we go ahead and look at number 2?
Yeah, that would be the best one.
Yeah, all right. So a lot of you actually asked me, hey, when did we ever do a problem like this? I think some of you saw this problem and went, what is this? Did we ever do this? I did something like this, this decomposition in the video, but also I think we went over at least one of these problems in class, this idea of decomposing. So the idea is we want to decompose it into 2 functions so that h, the function I'm giving you here, this function here, 2 times this square root of x squared plus 4, we want to make it so that that is f composed with g. So f is going to be like our outer function. And then g is going to be our inner function. Like that. So one common answer I saw, well, not super common, but common enough that I think it's worth talking about is this. This is not correct. So the reason that this is not correct is because these two things here, the 2 and this square root, they're being multiplied together in this function, right? So these two answers, the 2 functions that have been given here, these are not the functions that can be composed together, but rather functions that can be multiplied together to give us h. So this is yet again that same mistake of confusing composition with multiplication, okay? So that's why this is not correct. We can make it correct by putting an x factor right there. If you put 2 times x for your function f, and then for your g function, you give it the square root. And when you compose them together, when you compose these, f of g of x, what you end up doing is doing 2 times blank, right? Because you're going to take the g of x and stick it inside the f function. So this whole thing here, this whole thing here is going to go into that x right there. And then you get back that, which is the original function h of x that we started with. So that would work. That would work. So that's one answer. There's another common answer that I saw, which I'll just put up here, which is 2 times the square root of x. if you make your f of x your outer function, sort of like the outer shell, like the outer, like the armor, and then there's a person that goes inside it. Or you can tell I played Dungeons and Dragons, right? That's the first example that comes to my mind. I don't know why. It's like the outer shell, and then there's something that goes in it. I don't know. I can't think of a better analogy. But like, here's your f times the square root of x, right? And then you stick something inside there, and the thing that goes inside it is the x squared plus 4, right? So here's your g of x plus 4. That's what goes inside there, right? And that would squeeze in there and replace that x to give you the original one back again. So that is another good way to do it. There's other answers. There's other correct answers you could give, but there's 2 of them. Any questions on that idea?
Nope.
Folks, should we go over a quick example, like another example of either of these 2 topics? Decomposition or composition?
Did you say should we or can we?
Should we?
Sure.
Which one?
I guess for me, I'm indifferent.
Both. It's been a request for both. All right, let's move. Let's move here. Let's do some more things. I'm going to go ahead and clear the screen. Okay, real quick. If I do f opposed with g, that's going to be f of g of x. So first thing I can do here is replace the g of x with what it equals, outputs square root of x plus 5, right? And now I can write out my f function with a blank in place of where the x is, like that, x squared minus 2x plus 1, or blank squared minus 2 blank plus 1. Now I'm going to fill in that blank with this square root of x plus 5, square root of x plus 5, like that. Then I can simplify that a little wee bit, just a little bit, perhaps, to x plus 5, because the square root and the square are going to cancel each other out. Those are actually inverse functions, or for the most part, those are inverse functions, at least as long as x plus 5 is a positive number. Those are inverse functions. We get that, and then you can also combine the plus 5 and the plus 1 to be a plus 6 here. So we get like x plus 6 minus 2 times the square root of x plus 5. So that is the result of composing the function. That is a composition example. Okay, remember that you can also compose functions in the other order, and that generally gives you a different answer. So I'll just real quick show you that. If you compose the functions in the other order, like this, then we're talking about g of f of x. So the f of x is that x squared minus 2x plus 1, right? So so if you put that inside g, the g was, let's write out the g. Now we're swapping which one is the armor, right? Like it used to be that, no, it's a bad analogy. Which one is the shell on the outside? The f is the shell on the outside, one for the first one, but now the g is the shell on the outside. And so it's going to be, I got to write out g as you know, as a sort of like a blank empty shell, and now I'm going to put the f inside it, x squared minus 2x plus 1, squeezes inside there. And so the answer just ends up being this big square root with an x squared minus 2x plus 6 on the inside, and that's just from combining the plus 1 and the plus 1 again. So there's 2 different ways of composing in different orders, giving you 2 different answers. Right. So last one. Let's do another decomposition. Let's decompose this function. I'll call it h again. That's kind of nice because then we can use f and g for the pieces. Let's do something like x plus 5 cubed minus 1. That's a 3 cubed. So there's a function. We want to find f and g so that h equals f composed with g. Okay, would anyone like to suggest a function for f or g or both?
F would be x plus, or it would be x to the third minus 1. And then g of x would be x plus 5.
Folks, that look good? You can always check it by composing them together again. We want to compose them together specifically in the order that's suggested. Right, there we go. Okay, so the order that's specified here is f composed with g. So that means that g is on the inside and f is on the outside. So this thing here would go into there, producing hopefully this back again. Can you see it? I'm not going to write it all out in detail, but I can see it personally. I can see the format. So that's great. Good job. That is correct. That is a correct answer. Any questions on that, or anybody want to suggest another answer? Because there are other ways to do this. Actually, I can really only think of like one other reasonable way to do this. Yeah. Yeah, I can really only think of one. For the sake of time, I'll go ahead and just tell you what the other one is. That is another way you can do it, where the f of x is x minus 1. So it's basically just this whole chunk and then minus 1, right? And then the whole chunk there is the g of x function. Yeah. All right, folks. That's a little review of composition and decomposition. Almost 9 o'clock, so we've used about half an hour. That's good. We still have 45 minutes of class left. So, inverses. We might want to review inverses. Let's take a look at J. All right, topic J. I graded this one as well. And topic J, the first problem, I gave you a function, x plus 3 divided by x minus 5. Most of you did this great. Just want to real quick recap how to find an inverse for those of you who were confused about that. The best way to find an inverse is to write y equals our function x plus 3 over x minus 5, then swap the x and the y's. So all of the x's become y's and all of the y's are going to become x's. There's only one y, so that becomes an x, but all the x's become y's like that. And then you want to work on solving it for y. So try to solve it for y. So in order to do that, first thing I've done is multiplied both sides by y minus, it should be y minus 5, sorry. Let me fix that. Here we go. Y minus 5 times x equals y plus 3. And then we got to clear away those parentheses. So let's distribute the multiplication by x. We have xy minus 5x, or yx minus 5x or something, equals y plus 3. So now that we've cleared away all our parentheses, now we can gather together the terms that involve a y, right? xy, we'll subtract y from both sides. And then I'm going to get all the other terms over onto the other side. So we'll add the 5x to both sides. So I did that kind of quickly. But basically, the idea is to just kind of like reorganize it so that all the y terms are on one side and all of the non-y terms are on the other side. That's all. And so there's a little bit of changing of signs that happens as you add or subtract things from both sides, blah, blah, blah. Just shuffle things around. And then you say, haha, I have a y, I have this y in both terms on the left side, so we're going to factor it out. Y is now on the outside. What's left over is from the first term, you get an x left over, and from the second term, you get a -1 left over, right? Now, to solve for y, all we do is divide both sides by x minus 1, divide by x minus 1, and then we're good. So that cancels out. So now y equals this, and then you can say that's what f inverse is. F inverse of x equals 5x plus 3 over x minus 1. That's how you do that. Okay, and then you can check that f and f inverse, if you compose them together, they totally cancel each other out and just give you x. So some of you checked that, and I appreciated that. I didn't actually ask you to do that. Some of you did it anyway, and that was cool. That's great. So questions on that one?
How did you get the x minus 1?
Right, good question. So it came from right here. If I take out, I've got this y, right? And both of these terms have a y in them. But if I'm going to factor out that y, right, and pull it out here, outside these parentheses, I'm introducing these parentheses now, then what I have left over on the inside needs to be whatever factors were left after you remove the y factor. So if I move a y factor from the first term, I just have x left over, right? Then I have a minus, right? Minus. And then what is it that's left over when you remove y from y? There's like nothing else here, right? It's not 0, it's 1. Because you could have written this as y times 1. So that 1 is what's left over.
Oh, okay.
If you factor out a y or an x from a term which is just y or just x, then what you get left over is 1. It's kind of like, because when you're factoring, kind of what you're doing is dividing by that thing. So we're dividing by y, and y divided by y is 1, because it's something divided by itself. So you're dividing out the y from each term, and then you're putting the y on the outside of the parentheses. It's unmultiplying. You're unmultiplying or undistributing. Cool.
Yes, thank you.
Sure. Good question. Other questions?
Yeah, I just realized like on my quiz, I did went forward when you reach like the 5x plus 3 and x minus 1. I went forward and even tried to get something different.
Oh yeah, like further simplification beyond that point?
Yeah, that's what I just realized that I just keep going.
Okay, if you need me to take another look at it, let me know. Okay, if you think I misunderstood something.
No, it's like I don't think you did, but it's like I literally reached where you are right now.
Yeah.
And then I don't know for some reason if I missed the number or I didn't see it that clear, and I just read something like 3 plus 2x instead of 5x.
Oh, okay, that might not be a big deal.
Hmm.
Yeah, if it's just like a miscopying and something. Yeah, there's no, one thing to point out is like the goal here is just to get this function. Once we have this function, we're done. There's no solving of an equation to do any further. There's no numerical constant answer that we're looking for. It's like not like we're trying to solve for x or anything. That's a mistake people make sometimes, is trying to take this further and either simplify it further when it can't actually be simplified, or actually try to like set it equal to something and solve for x, which is just not what we're trying to do. So yeah, that came up more so with, well, actually didn't come up that much on I and J. I think that happened more last week, but I was pleased to see not so many people trying to do that this week, which is good. Yeah, it's important to break out of the mold. You spent so many years of math learning how to solve equations that now that we're not really doing that at the moment, it's hard to break out that habit. All right, the graph one, I do want to mention this graph one. We had this graph that was like 2, 3, 4, 1, 2, 3, 4. It had a point up here at 4, 4, and then it had a point up down here at 0, 2. Sorry, 2, 0. At a point at like 3, 1, 4, 4. So I gave you a graph that was basically like, let me see if I can me draw a good version of this graph. There we go. I gave you that graph, and I asked you to. I'm sorry. This is graph B. Graph B was the correct answer on problem 2. Graph A was not 1-to-1, so it doesn't have like a proper, like a complete inverse function. But graph B is 1-to-1, so it passes the horizontal line test. We should be able to invert it. So how do you invert it? That's the question. A lot of people just forgot to draw the inverse. So how do you invert? Well, you need to think about the line y equals x. This is the line y equals x. It's like a diagonal line at 45 degrees that's going to go through the origin. It's going to cross through the point 4, 4. So it passes through this point right here on the graph. What you want to do is reflect over that line. So this point at 2, 0 is going to flip over here to 0, 2. This point at 3, 1 is going to come over here to 1, 3. And the point at 4, 4 is going to stay right where it is because it's already on the line. And then the graph of the inverse is going to look like that. So that is how you draw the graph of an inverse, everybody. You always reflect over this diagonal line y equals x, whatever that happens to be. Sorry, whatever happens to be the result of reflecting. It's always that exact line that you reflect over. That's how you get the graph where all of the points are like the reflection of the inverse of the original points. You know, the point, like I was saying, the point 3, 1 is going to come over here to 1, 3, right? And the point 2, 0 is going to come over here to 0, 2. So that's what it means to do an inverse, because you're swapping the x and the y, right? Okay. All right. So transformations of functions. I'm going to stop sharing my screen for just a minute here. I think I'm recording the Zoom call, so it should be, yes, so here we go. That's good. So I'm just going to pull up an example to show everybody. And then I'm going to go over some transformations in Desmos here. Okay, I'm just snatching an example from one of my old quizzes. And I'm going to pull up Desmos. And we're going to go over some stuff. Oopsie. All right, there we go. Okay. Let's say you have a function, f of x equals x squared. My graph. So what I'm going to do, so right now, when you type into the Desmos f of x equals x squared, it immediately assumes that you're talking about graphing y equals f of x. Okay, but we can do that a little more explicitly, right? If you just turn this off, turn off the graph here by clicking this, it's not going to be graphing this. This is just going to sit here as a definition. Let's just let that chill out there and not graph it yet. That is just a definition of f of x. That's telling me what it means. Now, if I want to graph that, I could write y equals f of x like that, and that's going to be the graph. Okay, because this is the way I kind of like to think about it. This is a little more. Desmos just assumes that this is what you want to do if you write f of x equals x squared. But the way I like to think about it a little more rigorously is first you define how the function outputs are going to happen. So f of x is going to be defined by taking x and squaring it, get an output. And then you say, I want to graph that by having the y coordinates on my graph be associated with those output values. The y is going to equal f of x. So that's kind of I like to think of these as two separate steps. And it's useful to do that if you want to talk about transformations, as I'll show you in a minute. So now that we have this equation, y equals f of x, this is the graph of that equation. So this is y equals x squared. What we're seeing here is y equals x squared. Okay, this is a parabola. This is probably a pretty familiar graph. I imagine many of you have looked at this graph before. It goes through 0, 0. It goes through 1, 1, because 1 squared is 1. 2 squared is 4, right? So it goes through this point here at 2, 4. Kind of hard to grab, but there's a point there at 2, 4. And 3, 9 would be the next one, and 4, 16, and so on, right? And then it's symmetrical because squaring negative numbers is the same as squaring positive numbers, right? Okay, so the idea of transformations is I can take this graph, y equals f of x, let's make another version of it. And if I like subtract 3 from the x inside here, what happens is I've shifted this graph to the right. Right, so I've got this blue graph, which was the original. I'm going to make the original graph a dashed line here, and then this other version, which is shifted to the right. This is called a transformation. This is a shift transformation. If I subtract a number from x, it shifts to the right. If I add a number to x, it shifts to the left. So the reason that happens is essentially what you do to x, the graph has to shift in the opposite direction to like accommodate for what you did to the x. So if you're adding 3 to the x's, then to achieve the same behavior, your x's actually have to be 3 units smaller because that balances out the plus 3 that happens here. So all the x values on the graph are 3 units less than they used to be to balance out the plus 3 that you put. And they sort of cancel each other and bring you back to the original. That's kind of the way to think about it. So that's why whatever you do to x, if you add 3, it actually shifts left, sort of does the opposite on the graph. Does that kind of make sense, this idea of shifting left and right? If I add 2, it only shifts 2 units. I can add 2.7 and shift it 2.7 units to the left, right? Here we are at shifted 2.7 units to the left, okay? 1. If I add 0, then it doesn't go anywhere. It just shifts 0 units left or right. Does that make sense? This is called a transformation. This is a way to think about things. So since this is x squared, this could have been y equals parentheses x squared, like that, and then put an x plus 3 inside there. And you get the same idea. Here's shifting the graph 3 units to the left. Okay, this purple one now. Same thing, all right? It's just now instead of written out in terms of f with the x plus 3 on the inside like that, it's written out in terms of the square root, right? Or not the square root, the squaring function, right? The squaring function that defines f here. So now I've written it just explicitly with the squaring as opposed to in terms of the f definition. But these are the same, okay? Is that okay? If you want to take a graph and shift it left or right, that's what you do. Now, if you want to shift it up or down, you do the same thing, but you do it to y. If I add 3 to the y, I shift it down by 3 units for the same reason, right? That you've got to like accommodate for the plus 3 by making the y values 3 units smaller. It sort of balances out, it cancels out the plus 3. But since I added it to y, it affects the y values, right? If I do like -2, right, then it shifts all the y values up by 2 units. So now it's 2 units higher than it used to be, right? So that's how it works. Very straightforward. Now, here's where it gets complicated. With the y values, usually you want to solve it for y so that you can represent it as a function, right? Like g of x equals something. Usually you want to solve it for y. So you actually take the -2 from the left side of the equation, you add 2 to both sides, and you move it over there. F of x plus 2. Or if you were writing it in terms of the squaring function, like x squared plus 2, right? Like that. Now, because we moved it, because I just moved it from the left side to the right side, check this out again, it was -2 on the left side, it was y -2, and then you move it over, now it's +2 on the right side, okay? Because of that, now I'm adding 2, and that makes it shift up. So it seems like the way it works is the opposite of what it was with x. It seems like it's the opposite, right? But it's not actually the opposite. It's the only reason it looks opposite is because it got moved from the left side of the equation over onto the right side of the equation. That's the only reason it seems like the opposite. Okay. So because it got inverted when you moved it over. So it's like it was backwards originally, and then you inverted it and put it back to the original, back to what it, back so that it now agrees. So if you do x squared plus 2, it shifts up. X squared minus 2 is going to shift down, so on. Okay. So that is how you shift up and down. So I've shown you shifting left and right and shifting up and down. Now, what happens if I multiply x by something? Okay, let's say I want to write y equals f of x, except I want to multiply x by 2, like that. What just happened? What just happened to this graph? How is this graph different from the previous graph? It looks like it's sort of stretched out, maybe, or perhaps scrunched down. You can't really tell. It could be interpreted either way. Here's how I would interpret this. The original graph here had a point on it at like 1, 1, right? That point was on the original graph. What happens when you multiply x by 2 is that all the x values get cut in half. That point has been moved now to 1/2, comma 1. That's the point that's on the new graph over here. So check this out. It was at 1, 1, and now it's moved to 1/2, 1. What happens when you multiply x by 2 is you perform a transformation on the graph called scaling. Like basically adding and subtracting, it shifts the graph. Multiplying or dividing is going to scale the graph. And scaling means that all of the coordinates get multiplied by something. All of the x coordinates or all the y coordinates, one or the other, but not both. So in this case, because I multiplied the x variable by 2, I scaled all the x values. So all the x values are now half what they used to be. So like up here, here's an example. This used to be the point 2, 4 right here. And now it's been shifted over here, or sorry, scaled to be the point 1, 4, where the x value is half of what it used to be. And that's true all the way across this whole graph. Okay, if I wanted to double all the x values, then what I'd have to do is actually, instead of multiplying x by 2, I'd have to divide it by 2. If I divide it by 2, then you double all the x values. Again, just like with shifting, where what happens to the graph is sort of the opposite of what you did to the variable. So we have this. Does that make sense? That's scaling. Now, just like last time, just like with shifting, we can do it to x or we can do it to y. If we do it to y, same thing happens. So let's take the point 1, 1 and see what happens if you multiply y by 2. You multiply y by 2, and the y values actually get cut in half. So this is going to be the point 1, comma 1/2. Okay, like that. So originally it had the point 1, 1, and now it's shifted that point. I shouldn't say shifted. It's been scaled down to 1, comma 1/2. All the y coordinates get multiplied by 1/2 when you do that. But it's not usually written that way, right? Usually we want to have it solved for y, and we want to move everything over onto the right side of the equation. So instead, we write it as divide both sides by 2, and you have 1/2 times f of x. And so actually, this is just like with the shifting, where for the y values, it kind of does instead of doing the opposite, it kind of does the same, because you inverted it already to move it over to the right side of the equation. So if you take so here's how I want you to think about it. If you are doing something, if you're looking at a transformation of a graph, if you see something like a multiplication on the inside of that graph, that is happening to the x values. So this is cutting all the x values in half. That's cutting all the x values, like dividing all the x values by 3. But if you see something on the outside of the function, which is over here, right? This is the outside of the function. Then that is doing something to the y values. And in the case of the y values, you actually do exactly the same thing that you did to the equation, which is in this case multiplying by 3. So now all the y values are multiplied by 3. Okay, this is stretched it out vertically. Okay, that's doing something to the x values on the inside of the function. That's doing something to the y values on the outside of the function. That's shifting the x values on the inside of the function, and this is shifting the y values because this is on the outside of the function. So inside, outside. Does that make sense? What do you think, folks?
Yeah.
Pretty cool, huh? So I've showed you 2 different types of transformations that you can do. You can do shifts and you can do scaling. Now you can combine these things together. Like here, I've shifted to the, this has been shifted 3 units to the right, but it's also been scaled vertically by a factor of 4. So here's the resulting parabola that you get from that. Okay. Now, if you want to do a shift and a scale in the same direction, I'll show you how that works. Say I scale it up by 2, and then I'm going to shift it down by 3, like that. You really need to think of the scaling as happening first and the shifting is happening second. So if you're combining a shift and a scaling in the same direction, like as in both vertical or both horizontal, that's what I mean by the same direction. If you're combining them together, then you have to follow the order of operations. Multiplying versus adding. Which one do you do first? You multiply first, right? Remember PEMA or PEMDAS for those of you who might be a little older. That is the order of operations. Multiplying is always evaluated before addition, right? So the same rule applies here. If you're trying to graph something, then you always do your multiplying first, and then so you always do the scaling first, and then the shifting second. So that is a rule. Always scale first and shift last. Okay. There's one more type of transformation that I haven't told you about yet at all, and that is a reflection, and that has to do with negative numbers. If you multiply by a negative number, if you put it on the outside of the graph, that is making all the y coordinates flip their sign. So all the y coordinates are being multiplied by -1 here, if it's on the outside of the function. So negative f of x like this. That would be like if you wrote y equals -x squared, right? That is on the outside of the x squared function. So you're doing it to y. That reflects over the x-axis. If you look at the dotted line, the original one, and then this solid one, the new transformed version, the reflection has happened over the x-axis. It's like if the x-axis is like if you're looking at a lake, and the x-axis is the distant, like the far side of the lake, and this is like an object, then this is the reflection of that object in the lake, in the water, right? So the reflection, the line that you reflected over is like the surface of the lake. It is the x-axis in this case. Now, the other thing you can do is put the negative on the inside, like that. Put the negative on the inside, it's going to reflect over the y-axis. So in this case, it would be like putting parentheses around the x and then sticking a negative inside there, like that. You're reflecting over the y-axis. Now, for this graph, because it's x squared and it's already symmetrical over the y-axis, it's not going to do anything. So you can't actually, it's done something, but it doesn't really have, you can't see it because it's symmetrical already. So to show you what that looks like, I will just change our function here. Instead of x squared, let's look at like the square root of x. There we go. If I put the negative on the outside, it reflects over the y of the x-axis, that's vertical. But if I put the negative on the inside, it reflects over the y-axis, which is horizontal. So that's taking all of the x values and flipping their sign, and making them negative instead of positive. Okay. There's two different types of reflections that you can do as well. Reflections are like scaling, they're multiplying, so you also do those before the shifts. So even though I taught you about shifts first, you should always do the shifts last if you're actually like trying to perform the transformations on a graph. So now let's do that. Now, well, actually, before we do that, I want to show you this. So before we do that, let's just take a look at this example. So this is an example of a matching problem. This is the type of thing I've put on a quiz before. In the past, this is from like last year. So here I have five different graphs. This right here is supposed to be the parent function at the top. This graph at the top here is like, this is the original function here. And the idea is to thinking of this as your original function, what transformations are producing these different graphs? Each of these graphs is like one single transformation applied to the original one. And if this original function is called f, here are a bunch of different transformations in terms of f. So there's actually 1, 2, 3, 4, 5, 10. There's actually 10 different answers, possible answers, and only 5, there's only 5 graphs. So you have to just decide which of these is the correct transformation, like which of these is the correct equation for these 5 graphs. I'm going to give everybody a couple of minutes to look at this and try this on your own and see if you can figure out the answers. Folks, is this too small for you to read? Is it a little bit too small?
No.
Okay. I'm actually going to do something here. To make it a little easier anyway. Hopefully that's a little bit easier to read. If it was a little too small. I don't know if anybody's on a phone or something, but there we go. There we go. Oops. So you've got these possible answers on the left, and they're numbered 1 through 10. And then what I want you to do is match each of these graphs with exactly one of the answers from this answer bank over here. Okay, give that a shot. All right, if anybody has answers, go ahead and post them in the chat. Anything that you feel like confident about, go ahead and post it in the chat. So give me a letter and then a number 1 through 10 for which of the equations you think matches it. Then I will look in the chat, and so follow along and see, and then we can discuss them as we go. Okay. Your dog is making noises back there. Sorry. All right, folks, I'm not seeing any suggestions. Okay, is that because we're totally confused, or because we're just being quiet today? Totally confused is fine. Being totally confused when you first encounter a new subject is pretty normal, at least for a little while. You know, confusion is like a necessary step on the way to understanding, right? So if you're feeling confused, then, you know, that's not necessarily bad. You don't want to stay confused, right? You want to like get it eventually. All right, here, cool. All right, we have some answers coming in now. All right, great. Thanks, folks. It's 70, we have A4. Oh, 6, okay. Okay, so first, let's look at A. I've got one suggestion for A. That A might be 4. 4. That's this one. Okay, this is multiplying x by 1/2. That's what's been done here, right? So multiplying x by 1/2, what it should do is it should take all the x values and multiply them by not 1/2, but 2. So if you want to multiply, so that would multiply all the x values by 2, which would basically take this graph and it would like stretch it out, so it would look sort of like oh gosh, that's terrible. It would look sort of like this, as opposed to shrinking it down. This is like instead of starting at 1 where it originally was like that, it's like everything has been divided by 2 more so, right? Like this starts at 1/2, right? So this is more like it's been shrunk down horizontally and scrunched horizontally, right? So instead of 4, what should it be? For A here, we actually want 3. Let me switch colors so it's really easy to see what's going on. So for A, we actually want 3. Because what this is like, the original graph was this one. It went like that. And these points are half the x value that they used to be, right? those x values are cut in half. This is a key point. This, by the way, is a useful point, and this is a useful point, and this is a useful point. Those points are like key points that are kind of useful to pay attention to. So, so that was 3. Now, let's look next at B. Yeah, let's look next at B. I'm just gonna put myself on another layer here so that I can erase things. B, so what kind of transformation have we done to B? For B, one suggestion I'm seeing is 4. I also see the suggestion of 9 for B. Thoughts on that one? So for B, take a look at the key points. Key point, key point, key point. Those look very similar to the key points from the original graph over here. Remember, we have the original on the left over here. So very similar, except they're shifted, aren't they? It's moved up in the y direction. Yes, correct. So it's shifted up by 1. It's like the original points were down here, right? And they're all shifted up 1 unit. So that's the transformation. It's a shift up by 1 unit. And the answer we want for that is not something where we're multiplying, but something where we're either adding or subtracting. And since it's vertical, we're going to do it outside of the function, which narrows it down to one of these two. It's either going to be the +1 on the outside or the -1 on the outside. And so all you have to remember is which of those it is. And for our case, in this case, with that vertical shift, if you're going to go up by 1, you're going to actually add 1 on the outside of the function. So the correct answer there is number 9, like that. Okay. Here we go. Now, I did also see a suggestion for C. So next, switch colors again. Orange here, brown. For C, there's a suggestion to do 8, I think. Brown. Is this 8? All in Roman numerals here. VIII is 8. Is that right? Let's see. Look at our key points. Key point, key point, key point. Oh, this is such a terrible color. Very gross. Gross color. I don't like it. That's okay. I was going for orange, and I have dark orange, which is brown, basically. Yeah. I think that's right, isn't it? That's shifted. So what is this? This is the points used to be, looking at the original, they used to be at 1, like 0, 1, and 1, 0, and then over here. They've all been shifted to the right, right? Shifted to the right by 2 units. So shifting right 2 units should be taking x and subtracting 2 from the x, right? That right there. That's correct, isn't it? X minus 2 shifts us right by 2 units. That is perfect. So that is 8. All right, moving on. Now that we've done those first 3, folks, do you think you can figure out what the correct answer is for D? What should D be? First of all, are we scaling or shifting or reflecting? And then once we've identified if you're scaling or shifting or reflecting, then the question would be, well, by how much? Is this just a shift? It looks kind of like it's shifted up, right? Except this point down here is actually still on the axis, right? And our other key point would be somewhere up here. You can't really even see it. It's somewhere further up. So we really only have 2 key points that correspond to this point and this point right here. So it sort of looks like I'll give you a clue. It's really only one transformation. So one suggestion I see in the chat is to scale and shift. But I have kept all of these limited to just one transformation each. So I'm not combining anything yet. So this, in this case, this is, it's not shifting, because if it were shifting, then the relative position of these two points would stay the same. Like, you see how these are diagonally opposite one another by just one unit, like 1, 1 over 1 down 1. That relative position between them would stay the same if you're shifting, like in the case here, right? When you shift here, in B here, when you shift, the relative position of those 2 points stays the same, right? Down 1 over 1. And this shifting to the right on C here, relative position between those 2 points stays the same. They're over 1 down 1, right? But in this case, the relative position is quite different. Now it's over 1 down 2. So the thing that's changed is the vertical difference between those 2 points, and it has doubled, right? What we've done here is we've doubled all the y coordinates. So which of these answers, which of these equations over here tells us that we're doubling the y coordinates? Number 1. Trent suggests number 1. Anyone want to weigh in on that? Number 1, agreement, disagreement? Number 1 is multiplying f of x by 2, right? On the outside. So outside of f of x indicates that it should be a vertical effect of some kind, right? And so multiplying means it's scaling. So scaling vertically, first of all, and then if you're scaling vertically, you actually scale by the factor you multiply by, as opposed to its inverse. So if we're scaling vertically by 2, doubling y coordinates is another way to say that is, scale vertically by a factor of 2. That is indeed corresponding to number 1. So, Trent, you are correct. Number 1. And that brings us to our last one here. What is our last one? We've been dealing with a lot of shifts, and scaling here, but the last one is not a shift or a scale. What's this one?
Reflect.
That's right. This is a reflection. Now, are we reflecting over the y-axis or the x-axis?
X.
Yeah, over x-axis. So which one is that going to be?
It'd be the last one. So X or whatever, 10.
10, this one?
Yeah.
This is actually a -1. So rather than multiply.
Oh, I didn't see that.
So that's actually going to be.
So it would be 7. Is that 8? I meant 6.
6. Sorry. Yes. I don't know. Roman numerals. I apologize. I should. Yeah. 6. 6 has the negative on the inside. So inside is x, right, which makes it sound like that should be right. But when you reflect over the x-axis, actually what you're doing is making all of your y values the opposite of what they used to be. So all the y values are flipping back and forth. So the x values actually all stay the same. So you're not changing anything in the x direction. You're actually just changing in the y direction. So it sounds like because this says x-axis, it should be the x, but it's actually the y. So thank you, Miranda, for
No, it's okay. I thought in the notes that you said if it was in front of if the negative was in the front, it flipped over the y-axis, but I must have just been confused.
Yeah, no problem. Yeah, so flipping over the x-axis, this is more of a vertical flip. This is affecting the y coordinates, so we want the negative to be outside the function. So this is 5. All right. Thanks to everyone who participated in that. That was great. I hope you all find that I feel like this matching thing kind of helps to get things straight. I hope. This is going to be up on YouTube, so you can see everything. You'll be able to check this out later if you want to when you're studying. Okay, so it's 9:40, so we have not a whole lot of time left. This is good. I mean, we did a lot with transformations. The only other topic we're doing this week is linear models, which I think is going to be an easier subject. So we can talk about linear models a little bit on Thursday before the quiz. Folks, shall we do one more example on transformations before we end today? You up for it? I don't want to push you too hard. This has been probably a lot to take in. I'm going to try. We're going to try doing one thing here. We're going to try doing something. I don't think this is going to take a long time. Let's see. All right. Here we go. Copy that. Come over here. Okay, I'm going to clear the screen. All right. So remember, you're not going to lose this example. This example is going to be up on the YouTube video, so we're not going to lose that. Here we go. All right. And now, yeah. Let's do this. Okay. Sure. Let's say the graph we're looking at here. This is the graph of let's call it f of x. What I'm going to do is I'm going to define another graph, another function. In terms of f, it is going to be negative f of x plus 4 minus 1. No. Let's put sorry, 2f of x plus 4. Here we go. Do that. That's what I wanted. Okay, so what is this going to do? What is this going to do? This is going to do several things. All right. So looking at over here, let's start with the scaling. So forget the plus 4. The plus 4 is a shift. That is going to happen later. Let's do that last. The first thing I want to do is either scale or reflect. So there is a negative out here. So this is going to reflect vertical, which is over the x-axis. That is something that's going to happen, right? So to reflect over the x-axis, what I'm going to do is take every point on this graph and I'm going to flip it down. So the point at 1, 1 is going to become 1, negative 1. And the point here at 4, 2 is going to become 4, negative 2, and so on. So what I'm going to get is I'm going to get this graph. And so on, like that. Right, so this is this point here, came down to this point here. This 9, 3. Now we're down here at 9, negative 3. Okay, whoops, I switched to gray. Okay, so that's our step 1. Does that make sense? I'm going to switch to blue. Step 2. Sorry, purple. This is step 1. Okay, so I'm just going to do. I'm doing these transformations one at a time. So the next transformation I want to do, let's focus on the multiplying by 2 here. So far I've looked at the multiplying by negative 1, negative there on the outside. Now this multiplying by 2 is going to be a scaling of some kind. Since it's outside the function, it's going to be vertical. So scale vertically, and the factor is going to be 2. In other words, that's going to double all the y coordinates. So starting from where I was before, I'm now going to double them. So this 1, -1 is going to come down here to 1, -2. That's taking that y coordinate and doubling it. The point 0, 0 is going to stay right where it is. That's not going to move anywhere because it's multiplying multiplying 0 by 2 isn't going to change the value, right? Let's see, this point at 4, -2 is going to come down here to 4, -4, right? I'm multiplying all the y coordinates by 2. This point, 9, -3 is going to come way down here to 9, -6. So my new graph is going to look like this. And that is graph 2. Okay, so we had 1, and then now we have 2. And next, do graph 3. So the third thing is to look at the fact that we have this +4 on the inside here now. Okay. Yeah, +4. So we've covered the reflecting, we've done the scaling, and now we're gonna do a shift. The shift, since it's to x, it's going to be horizontal, right? It's going to be horizontal of some way because x is horizontal, right? X is our horizontal axis here. It's the x. So what we're going to do is shift either left or right. And for the x, anything that's horizontal, you always have to invert the direction, right? You always have to change the direction. So this says +4. That means you're actually going to shift left by 4 units. So all these units, we're going to subtract 4 from the x coordinate. So this point at 0, 0 is going to come over here to -4, 0. And then the point here at 1, -2 is going to come over here to -3, -2. This point at 4, -4, shifting 4 units to the left is going to come here at 0, -4. And then this point 9, -6 is going to come over here to 5, -6. And this graph here is the result of graph of that third transformation. Okay. So what I've shown you here is an example of taking some original function g, taking this original function f, right? This is the function f right here. And then taking that graph and transforming it, right? We had the f, and then we took that and we performed these transformations on it. Okay. We have a subtraction. We have or rather not a subtraction. We have a negative sign here. Okay. That did a reflection. We had the reflection 1. We had the scaling, which was the multiplication by 2. And then we had the shifting, which was the addition of 4 that was inside over there, okay? So that produces the final graph. The final graph is this sort of like teal one here, which is y, that's the graph of y equals g of x, okay? It's the result of doing all 3 of those transformations, one after another. So first flip down, then stretch out, and then move to the left, right? That's how you apply transformations to an actual graph. Okay. Okay, so that's all we have time for. I'll go ahead and save this and send this picture out to you if you want, along with the video that I'm going to post up on YouTube. So I'm going to stop my recording now.